Hello. In this video, we are going to try and obtain the capacitance of a parallel plate capacitor having a diagonally filled dielectric medium, in fact, two of them, one with a dielectric constant epsilon R1 and the other with a dielectric constant epsilon R2, and the given, well, I'll say width of the plate here is L, and the depth, as you can see, as you cannot see in the picture over here, is B. It runs into the sheet that you're looking on your screen, and then the separation between the plates is obviously D. So what we are going to do is we are going to consider a step-by-step process involving involving the taking of a strip out of that given arrangement, and then we integrate that strip from across the given width, or rather over here you can see as the length L. So I'm going to draw another diagram. So this is the same thing that I'll be just showing you, taking the strip consideration into account. So here I am considering the strip. So one of the plates is obviously positive, the other one is negative. And here is that thin strip that we are going to consider infinitesimally thin. And that is dx, that is the width of that strip. Remember that the depth of the plate that you are not able to see in this two-dimensional figure, that runs into the plane of the screen or the sheet present in your screen, that is going to give that is B. And so the area of that strip that we have considered, the area of the plate exposed due to that strip, is going to be B times of dx. So that is dA, small area for that small strip. Now if I'm considering this strip from a distance x from one end, then obviously at the other end I'll have L minus x. So this is x, the top. At the top we are obviously going to have x as well, and so what we get is at this point, at this division point, we are going to have a distance which is going to be the perpendicular of a triangle, let us say having an angle theta. So both those corners I am going to keep the angle as theta. So that length, that perpendicular, is obviously going to be base times of tan theta, base here being the value x. So this is x tan theta, and the other one is obviously the distance d minus x tan theta. So this is going to be d minus x tan theta. Now with this provided, with this information in our hand, we'll just obtain the capacitance. As we can see, this is a series combination, because at one end of the plate, suppose this end you are having the positive end, and it'll be the negative end of the closing side in that diagonal point, and then we will follow it up with another positive followed by the negative at the other end at a distance d. So this is an end-to-end connection, and obviously this is a series combination. And in series combination, in case of capacitance, the net capacitance will be 1 over dc, d showing that the value is really small considering the infinitesimal cases that we have taken. So 1 over dc is the equivalent capacitance, and then we have 1 over dc1 for the, let's say this is dc1, and this is the top one is dc2, so dc2 over here. So 1 over dc1 and 1 over dc2. What are the values of dc1 and dc2? Let's see over here. dc1 is, again, the slant of that strip is not going to affect that infinitesimal portion, so we are going to take it as a straight portion. So for this parallel plate capacitor with a dielectric epsilon r1, we have epsilon r1 times of epsilon naught times of the area. In this case is, as I told you, b, that is the depth, and that multiplied with the thickness dx, divided by the length between the two plates. In this case, the two plates is that division, the second, the division, the bottommost plate over here, and the division till here, the distance is going to be d minus x tan theta. So d minus x tan theta. And what about dc2? Well, dc2 is equal to epsilon r2 times of epsilon naught times of the area, again is b times of dx, over the distance. In that case, as I had already mentioned, this is x tan theta. So we put these values over here, and what we get is 1 over dc is going to give us, well, we can obviously, in the denominator we have a few common terms, and out of that we have epsilon naught b dx, they can be taken out, and because we are taking the reciprocal of them, and for the first one we have d minus x tan theta, and in the denominator we have epsilon r1, plus the other one being equal to x tan theta simply over epsilon r2. So this is going to be the net capacitance, or the reciprocal of the capacitance in this case. So the net capacitance dc of that infinitesimal capacitor is going to be epsilon naught b dx taken to the top, and then we can take the LCM over here and then take the reciprocal. So obviously LCM is going to be epsilon r1 times of epsilon r2, and that's going to go to the top, and then that was multiplied to these two terms over here. So we have epsilon r2 times of d plus, not plus, minus epsilon r2 times of x tan theta, and then we have plus epsilon r1 times of x tan theta. So this is what we have ended up with for the infinitesimal term, right? Now we'll consider taking the integration to obtain the value of the entire capacitor at hand. Now what do we do? So we take the epsilon naught b dx as it is, and actually the dx is going to be integrated, so we'll just strike it out from here, and we take out that epsilon r1 and epsilon r2 from that square bracket, and in the denominator what you will find is, I'll take it out gradually, that if we have this x tan theta as the common factor to those two terms over there, so we have epsilon r2 times of d, and then what we do is we take a plus of the epsilon r1 minus epsilon r2, and we take x tan theta as the common term. Pretty straightforward, there's no problem with that. In the figure, if you see the angle theta, I can put the angle theta over here as well, in that red portion that you see here. I have put theta now, and this theta, as you can see, is the perpendicular over base, that is equal to d over L. So I can use that value of tan theta over there, and I write it directly. I erase that term over there, tan theta, and instead of tan theta I write the term d over L, d over L. I I'll use d over l. So this is d over l. Now there are two d's in which can be taken common, obviously. So again, I erase it from that point and I take those d's out of that denominator term and I put it over here. Now, because you have this depth b as the depth and the l being the length, so b times of l is going to give me the area of cross section. What I'm going to do is that l in the denominator that is present over there, that goes as the LCM, so l gets multiplied over here and then goes out over here, which goes up to get multiplied with b, which goes up to get multiplied with b. Let me multiply that. So now you have b times of l. And what is b times of l? As I told you, b is the depth of that sheet of capacitor plate and l is the length that you are viewing here as the width. So that depth over here and that multiplied to the l is going to give me the area of cross section. So b times of l is going to give me the area of cross section, so I write it over here as a. So I have epsilon naught times of a, epsilon r1, epsilon r2 over d, and the dx term, which carries the x, that with the denominator, complete denominator term, that will be integrated to get the total capacitance. So the total capacitance is going to be C, which is equal to integration, well, all these terms over here, epsilon naught a over d times epsilon r1, epsilon r2 are going to stay out, and this is going to be integrated from 0 to L with the dx at the top, and at the bottom we have epsilon r times epsilon r2 times of L plus epsilon r1 minus epsilon r2 times of x. Now obviously 1 over x is going to give us ln x when integrated. Dx over x is going to give us ln x, but here we have some additional term to that, so we follow the integration rule. If in case there was an epsilon r1 minus epsilon r2 at the top, then this will be in logarithmic form, and in order to bring this term over here, we simply divide it over here. So if I have multiplied that term over there, then I divide the same thing over here because they do not involve any x in them, so they are out of the integration term. So this is divided on this side. So now what we get is epsilon naught times of a over d, epsilon r1, epsilon r2 over epsilon r1 minus epsilon r2, and then this is simply ln of epsilon r2 times of L plus epsilon r1 minus epsilon r2 times of x, taken from 0 to L. Now the only term that involves the L is obviously the x term. I mean the L is going to be used in that term. So what we get is again epsilon naught times of a over d er1 er2 minus dielectric 1 minus dielectric 2. Then in the logarithm we have er2 L plus the 0 is obviously going to give me 0, so I'm just going to put the L for x. So we have er1 times of L minus er2 times of L. Now er2 times of L in the plus and minus are going to cancel out, so we are left with ln er1 times of L. Okay, there's also going to be another term for the zero because the logarithm is being used for the uh, entire term in that square bracket. So if I put 0 in the next case, although the x is going to 0, the second term is vanishing, but the first term still remains. That is, we are going to have minus of log epsilon r2 times of L. That is still going to be there. Although the second term is vanishing because x is going to be taken as 0. So we have to put that as well. Now, what we are left with is ln er1 L in this case and ln er2 L. So, and that's the minus part. So obviously when we have ln a minus ln b, that's going to be ln a over b. So the what we are going to end up with, we can take epsilon naught times of a over d as c naught. So the final expression for the equivalent capacitance of that diagonal arrangement is going to be c naught epsilon r1 epsilon r2 over epsilon r1 minus epsilon r2, and then we have ln epsilon r1 L over epsilon r2 L. The L's are going to cancel out obviously, so we have epsilon r1 over epsilon r2. This is the expression for the equivalent capacitance of such an arrangement involving two dielectrics filling the distance between the plates diagonally. So that's all from this video. We'll be trying more such numericals, brainstorming stuff. Till then, thank you for watching.